All right, today we're going to continue our talk on Unit 0, more specifically Unit 0.5, and getting a little bit into more vectors. Last time we talked about vectors having both direction and magnitude. Oh yeah. So that's what we'll talk a little bit more about, and it becomes the more we talk. I think it was we kind of changed some things up. We talked about vectors early on, and I think that's a good thing because we tend to use vectors the rest of the year. So magnitude and the coordinate system, we've talked about that, I think, at great length. It's not just a suggestion, it is kind of becomes a thing. Remember, your ability or lack thereof to draw things is not dependent upon the correctness of the answer. And sometimes drawing out what you are thinking is the important part of these vector problems, and almost all problems in physics. A lot of it can come down to how are people looking at the problem. So drawing it out is so important. In the vector lab, you will be asked to draw them out. You'll be asked to make measurements and then do the other part and do the calculation as opposed to just drawing it out and measuring it. And you'll be asked to do kind of a comparison of the error, lack thereof, involved with that. So, and again, drawing out what you need to do is so important. Now, our book is a little bit hard because some books or other reference material, we have two books technically for this class. The one that I've put together doesn't have as many of the colors with it because of the whole printing thing. If you go into most other materials, we do have some of the older versions of books. They have colors, and it would not be a bad idea to get yourself some color pencils so that you can kind of help yourself out. Now, in doing notes, it's going to make my life is made somewhat easy because I have the ability to change the color of the arrows and things that I'm drawing with using that. Some of the ones that we try to at least hold ourselves to: displacement is green, velocity is red, acceleration is purple, and forces are blue. Those are, for the most part, pretty standard ones. You might see displacement and velocity switched. I've seen it before. You just have to pay attention to the reference material that you're using. In some ways, it will allow you to visually see what you're drawing. One of the things why we do this is because in physics we like a lot of subscripts, and we try to identify all the arrows that are involved. It might help trying to figure out some things. It would not be beyond physics to have a wonderful object and then all of a sudden you're going, okay, it's moved that far, and then it's moving that fast. It has this force, and maybe a little small one over here. And let's change the color. And therefore it's accelerating that way. There's a lot going on there, a lot of different colored arrows. It's not because somebody just decided to puke up a rainbow. It's because the box went so far, the green arrow usually started out, but the velocity of the red arrow, the blue arrows indicate the forces that are present on the box. And because the blue arrows don't match up, there has to be an acceleration in the direction of the largest blue arrow. There's a lot going on there. Not only that, we ultimately should label every single arrow as well. There gets to be a lot. So those of you that are colorblind, I apologize. But it does kind of tell a little bit more of the story once you start seeing with those arrows and get more practice with them. Okay? It does, if you get into electronics, sometimes finding your circular, your paths for your circuits can also be used with green, reds and blues and all the other colors. But it is a common thing to use different colors. Because things can very greatly change if that box was going up an incline. And things really kind of get a little cray-cray, so to speak. Okay? Some of the first vector additions are simple. And this is why we're kind of adding it when we're doing it. I think easy at vector additions is vector additions in one dimension. You're just either adding or subtracting. Just like in math class back in your elementary days, that's what you started with. Started with your additions and your subtractions. I've seen elementary teachers use Gus the plus and Linus the minus to help kids word associate, make it fun, because they talk about addition and subtraction at great lengths, because it is very important to at least get that started. It's hard to balance a checkbook without knowing how to add and subtract. Someone who does not have a great understanding of adding and subtracting should definitely not be an accountant. Multiplying and dividing would also be quite the necessity too, but we'll get into that as we go. And so now we become into the resultant, and that is, where do you know? How do you know which is which? Making sure that your signs. Now in the top example, we see that an object goes 14 kilometers east total. Which means, how it got there, we don't know, and that's where the other arrows come into play, where it went 8 kilometers. Maybe it stopped, had lunch. Maybe it was a bathroom break. I don't know. Whatever it is. Then finished off and went 6 kilometers. add those together is pretty easy. Now, in the second one, it goes 8 kilometers, went, oh crap, we're going to run out of gas, turns around and starts going back to the gas station. And then runs out of gas after 6 kilometers going back. So therefore, how far from the gas station did the person go? One could think. Well, they're 2 kilometers east of the gas station. So how it gets added is as simple as just that. Now what happens is we don't have just labels anymore. There's a directional component to it. It went 14 kilometers east, and it is 2 kilometers east of the place that it wanted to go to. A lot of times it's the origin. The place that we move and we talk about, and that's at the beginning. Okay? Place at the beginning. But life isn't always easy and nice. A lot of times it's messy. And therefore we can also have motion in 2 dimensions. Triangles. For most of us, right triangles are best case scenario. Right triangles meaning that there's a 90 degree. Now sometimes we're not going to be told that it's 90 degrees, so we have to be careful. We have to be careful. How we add them together, as we can see, doesn't really matter all that much. The resultant ends up being the same. Whether you go run over rise, or run and rise, or rise and run. As long as you run, you don't write it as you rise. But even then, you could get the right answer. You're just going to have to change some things a little bit. So that's the nice thing about sometimes putting these triangles together. The order in which you put them together does not matter. And that is one of the things that you do in the pencil and paper part of vector is the pencil and paper part of it. Is you put them in different orders. And you're going to have to get things to have a triangle. Otherwise you're going to have things you're like, I don't know how to solve that triangle. Because it doesn't look like a triangle. So you have to add them together to put it and find, like, well, if I find this triangle, I can find this triangle, and then I can find this triangle. And that becomes the thing that we do very frequently, is adding our stuff. Now, one of the other things that we have here is, how do we do a directional component of this? Well, a lot of times you're going to say that this would be, or at least this angle here that we have is north of east. Okay. Because it is moving in the north part. Okay, it's moving into the north part of east. Now, what can be confusing is what do we do with this other one up here, the top? Is it also north of east? Yes, but sometimes people want to call it east of north. We're kind of moving down or south of, but that kind of, the south part would mean that quadrant. And so we have to be very careful about that. It's one of the things as we move forward that becomes a thing. And I think in the practice problems and the homework, I actually say do it as this of this. Don't say the actual direction, but blank of blank at whatever degrees. So pay attention to that. I do have that written in there. So let's try an example. All right. In the morning, you walk 3 blocks east. I'm going to point my start. 1, 2, 3. Then I go 6 blocks north. Oh, crap. 1, 2, 3, 4, 5, and 6. And then 2 blocks east. And then 1 block south. What is your total displacement? Distance and direction. Now, this is where also some colors can help us. That's what we're solving for, the black line. Did we have to add those vectors in that same order? No. But what makes life helpful is drawing it out as it's being done, at least for a beginning. Then you look at it and say, well, this isn't that bad. I can add this in a different manner to give me the same exact one. Because a lot of us, drawn in a different color of green, hopefully. Can see that this arrow here could be drawn down right down there, right? And nothing's different. We can also maybe see that this arrow here could have been drawn anywhere else. It could have went south. Because what does it end up doing with these two numbers here? They end up canceling each other out, don't they? So I would end up having this purple color looking to give me my ultimately what that is. Where I have 5 by 5. 5 blocks east. And 5 blocks north. And I'm going to guess the majority of you would know how to solve for the black line, where we would have a squared plus b squared equals c squared. 25 plus 25 equals c squared. 50 equals c squared. And then I need to take the square root. And then some people will go, okay, then the answer would be square root of 50 is equal to c. And some of us that don't like that as an answer would say, no, let's just put it in the decimal number because that's the normal way people do things. And that would be 7.7. That would say that it is, let's say, I'd say 7.7 blocks northeast. What direction does that arrow point? From the origin, it would be northeast. So 7.07 blocks northeast is what we would say is our C in this thing. But like I said, Pythagorean theorem, you probably looked at it and you're like, okay, I just do that. And you would do it probably just naturally. But we still want to walk through and say, hey, remember the Pythagorean theorem? Yeah, remember when that used to be a thing? Yeah, we're still going to keep it. Okay? Are there other ways in which this can be solved for? Yes. That's what makes physics sometimes frustrating. 4 people in a group. All of you are solving it in a different way. All of you get the right answer. That's what makes this frustrating sometimes. Some of you will find that you like to do things very methodical, and some of you will skip steps. Then some of you that skip steps will find out, ooh, I can't skip steps all the time. Some steps can't be skipped. You have to do them still. So here's another example, and it does not matter the order in which we do them, but the how we add these vectors together does matter. How we add them together does matter. The tip to tail method. Now when we go to solve for the resultant in this vector, doesn't look straightforward, does it? This is one of those ones where we get to find something to find something. Those of you that will be doing the paper and pencil part of the lab will probably want to make sure that you have access to your book, because the equation that you'll need to be able to use Pythagorean theorem. It's in there, I think, and also law of cosine, at least law of cosine. I prefer that one over law of sine. I always mess things up and put things in the wrong ratio for the law of sine. So here would be one, and I would personally solve this one probably. Find the green arrow, because that one will be easy first, right? Then after I find that one, I have I should have the ability to find the other parts that I might need. Because then now I have two triangles there. Solve for the easy triangle, get what you need, then solve for the harder ones. But, doesn't matter. What we're looking at for this slide here is, does the order in which I put these together matter? I do this right. So this is where it gets off hand just a little bit every now and then. Okay. Let's add it's unfortunate. The goodie. Okay. So they went 1, 2. So let's go 2, 1, 3. Now, obviously, because of some slight arrow issues, we have some of that, of why this may or may not be completely exactly the same. However, that green arrow should be the same as that. Let's see if I can cut it out correctly. And it's not so far off, is it? When we put it all together. That's the idea, is it does not matter the order. Now, which one does this one doesn't look too fun to solve, does it? Now, one of the other things that would make this a lot easier to solve was, wouldn't this be nice if they said an angle there? And now all of a sudden, just like the floodgates open up and how you could solve it was a lot easier. Because if you know, and here's the other fun factoid, right? If we know that angle, that means we're also going to know what? Oh, I did that. I'll also know that angle, right? I forgot the geometry term on the why it is, but it's true, trust me. Okay? And if we know those two angles, that means we actually even will know that angle and that angle, right? So it kind of becomes that if I know one thing, I can try to use, and this is where, again, we are going to make math useful. And that's the important thing.